So next up is question 7. This one's problem 34 on page 617 of the textbook. And it reads, for a demonstration, a professor uses a razor blade to cut a thin slit in a piece of aluminum foil. When she shines a laser pointer, lambda equals 680 nanometers, through the slit onto a screen 5.5 meters away, a diffraction pattern appears. The bright band in the center of the pattern is 8 centimeters wide. What is the width of the slit? So again, the first thing we want to do is think about what type of diffraction are we talking about here. In the problem, it states that the professor is cutting a slit into the paper, and there's only one slit that's being cut, so that means we have to have single slit diffraction. Now our next step is to identify what pieces of information we know. So we know our wavelength is lambda is equal to 680 nanometers. We're told that our screen is 5.5 meters away, so we're going to have L equals 5.5 meters. And then the bright band in the center of the pattern is 8 centimeters wide. That's going to be the width of our central maximum. So that was something people sometimes had trouble identifying what that 8 centimeters was. That's our W, the width of the central maximum, and that's 8 centimeters. Now if we want to solve this problem, we're going to use the equation for the width of the central maximum because we're given information about that, so that's probably an important thing. And so recall from Wednesday's lecture that we had W is equal to 2 lambda L over A. So L is our distance from our screen, lambda is our wavelength, and A, that's the width of our slit. So it's a little confusing. We have a W that's a width and an A that's a width, and they're different things, but W is the central maximum's width, A is the width of the slit. We're trying to solve for A, so we're going to multiply both sides by A and divide by W. And so we're going to get that A is equal to 2 lambda L over W. Now from here, it's just a matter of plugging in our values. So we're going to have A is equal to 2 times 5.5 meters. Now our wavelength is going to be 6.8 times 10 to the minus 7 meters. And then 8 centimeters, that's the same thing as 0.08 meters. So now we're going to plug this into our calculator, and we're going to find that A is equal to 9.4 times 10 to the minus 5 meters to 2 sig figs. So again, I think one of the trickiest things from this homework set was just figuring out what type of diffraction you're talking about, and correspondingly which equations are you okay to use here and which ones aren't going to work here. So as you're reviewing these questions, make sure to pay attention to what section you're in, what equations are valid for the section, and what equations are not.